Jordan has over 14 years of experience working as regional manager, project manager, and engineer, diver, and team leader with Collins Engineering, specializing in several areas of inspection. He has performed thousands of underwater structural inspections using commercial diving techniques and numerous inspections using various acoustic imaging systems.
Well, thanks everybody. This one will be a little bit different because it's going to be more inspection focused than the ones previously, but hopefully you find it informative. So this is identification of hidden deficiencies in timber elements using resistance drills, so we'll go into what that is. Pretty much already gave my background, but just very inspection focused for about 14 years now, so have some experience. A lot of it was diving, but then a lot of inspection work and using tools like the resistance drill that we'll talk about. So I'm gonna go on a journey that starts with an overview of timber bridges, what are some of the challenges with them, what is resistance drilling before we actually go into, what is the tool, how does it work, how do you interpret the data, some best practices and limitations, and then finally some case studies. So it's a lot of ground to cover. It's normally an hour-long presentation, but I'll try to keep it moving. Most of you here might have a pretty good idea about timber bridges already, but the key points are kind of that there's a lot of them. They've been around for a long time, and most of them are getting pretty old, so it's a problem that most owners have to deal with. I think this data on this slide might be slightly out of date, but you get the idea that there's tens of thousands of them in the United States still, and they're a significant percentage of the national bridge inventory. This is why we do what we do, which is to avoid bridge failures, obviously. Many of these timber bridges were built by the Civilian Conservation Corps 70 plus years ago. So these particular failures prompted this client to do detailed inspections of all their timber bridges because they were near at the end of their lifespans by potentially 20 plus years. So the defects that caused these failures were not detected until it was too late, which resulted in the failure of the element and required emergency repairs. So we can use the information that we get from the timber inspections, the budget ahead of time, and start planning. Basically, it's to avoid risk, get ahead of the decay. The old adage, an ounce of prevention is worth a pound of cure. So what are some of the challenges? Common defects that we look out for you might be familiar with. We got check splits, cracks, decay, crushing. Some of these are easily confused with each other. They're just words. It's not as clear cut maybe as some of the defects you see in steel or concrete. A lot of time the crushing is a result of decay, even though it's technically mechanical damage. A lot of times there's eternal defects in timber that's hard to detect, something that's not on the surface, like a check. So the traditional methods, and gotta give some credit to the Minnesota DOT actually, because this is from their manual, and they have a lot of good information on timber inspection out there if you want to research a little further. But anyone that's done a lot of inspection work knows that most of it's done by hitting a piece of timber with a hammer or sticking a pick in it, using your ear to try to detect differences in sound, hollow sounding timber. If you've read inspection reports, a lot of times it'll just say like timber sounded hollow. It's not very quantitative. It's an indication that you should investigate something further. So the tool on the left there is an awl, and then you got your hammer on the right. There are some advanced methods, stress wave timing and things like that, if you want to research a little bit further, but these are the basic things that every inspector will have in their truck. The other kind of method, it's called an increment borer, which is seen here. It's basically a little drill that's hollow. It was originally made for foresters or arborists to check trees, but us engineers started using them to inspect timber structures. But it's a bit slow, it's laborious. There's some technique to it, especially if you use them underwater when you're diving. Typically doesn't go all the way through the member, just halfway. Sometimes the resistance can get too great to turn it. It's more destructive, 3/8 of an inch to up to 3/4 of an inch, so you need to plug the holes with treated dowel. One advantage is that you can actually use it to identify the species of the tree. But that was pretty much the state of the art for a long time. Here's an example of some increment cores that I took on a project in Marquette, Michigan. They're all from the same structure. Pretty labor intensive to get these. They're all underwater. It was a bit destructive. As you can see from it, it's all the same structure, but it's highly subjective because you can see how different each of these cores looks. It can be difficult to detect the extent and the severity of the decay. It can be hard to quantify the amount of decay because it kind of all pushes together as you're taking the core, so you can't measure the extent of the rot if there is rot. Basically, all of these piles looked and felt the same from the outside and seemed sound from a visual and tactile inspection, but got vastly different results. Some of them look like they're treated or not treated. Some look like they're totally in perfect condition. Some look like they have creosote. So it's very variable. How do you rate timber? This is just one example of like how you would go about quantifying defects in timber. It can be difficult to determine the condition if you don't know what's happening internally, and the timber rating varies by agency. This example is not an NBI example, but it's a pretty good visual example of how we basically categorize these different levels of defects in timber. And we'll kind of see how that ties back to how we can improve that with the resistograph. So what is the resistance drilling? I actually got another quote from Minnesota on here, but basically it's a tool that'll help you identify things before they're bad, so you can get the funds in place to replace them ahead of time, right? Like work smarter. This is the IML Resi PD500, which is the actual unit that we use. Resistograph's the brand name. This allows you to put a number to the less quantitative data, the kind of things that we talked about earlier. Simply put, it's a drill, records the resistance required to drill through a piece of wood digitally. The resistance is related to the density. Basically, it's very accurate, very quantitative, basically the exact opposite of the old inspection methods of yesteryear. Negligible impact on the overall structural system, minimally invasive. We call it quasi-non-destructive due to the small size of the drill bits. This actually has been around technically since the 80s. It was intended for loggers and foresters as well, and it's another thing that we've adapted for engineering. Here's a quick view of what it looks like. Pretty simple machine. It's got a knob on top, 2 buttons. Uses regular off-the-shelf batteries for Bosch power tools. It's made in Germany, this one. So it has an output that's displayed on the screen on front there, and it can wirelessly transmit the data to your phone or laptop if you want through Bluetooth. So we actually work with IML quite a bit on kind of continuously trying to improve these. They're pretty good at working with us. A little bit of information on the operation here. This is the view of the display on the unit. You can see the drill curve in real time as you're drilling, so you know if you're getting good data or not. So you can basically, it will record and store each measurement as you take it on the machine. You can go back and view them. It has some built-in software that can actually automatically pass-fail something that you're inspecting. That's like more of a power company thing. But you can basically input parameters for the amount of decay, and then it'll basically tell you if your member has failed or not. But gives you all the information you need there: rotation, drilling depth. It can auto retract, your tilt, and all that good stuff. Here's an example of it actually being used. On the left there, above the scale, that's the actual needle. It's 1.5 millimeters, so it's pretty small, very flexible. It's about 19 inches long. I think the longest one that they make. The unit comes with a carrying strap. Got to make sure that it's in a pretty stable position, and you have to depress it against the piece of timber for the whole time that it's working. But it's pretty fast, as you'll see here in a second. Yeah, so this is actually a video of it in action, and it's not the most exciting thing, but you'll see that this little clip is about 30 seconds long, and that's how long it takes to get one measurement. It drills through the batter boards and the pile behind it. So using the old hammer-all method, you can inspect timber piles that are behind batter boards. So this way you can get some information on those and drill through the whole pile. Something that we weren't able to do before, collect a significant amount of data in a short amount of time, basically. So there, that's it, that's done, one measurement. And there's the picture of the size hole after it's done. Pretty hard to see. Like I said, quasi-non-destructive. According to the manufacturer, these actually do self-backfill, but depending on the client, some clients will want you to maybe put a little bit of silicone sealant or marine adhesive in there just to make sure that it's sealed up. So there's also an underwater unit too. It's actually an electric drill, just like the above water unit, but it uses compressed air to keep the internals dry. So we have one of those too. This is what it looks like when it's all assembled. You got a generator, you got your low pressure compressor, there's the hand unit that the diver holds, and then there's the topside unit that controls it, so they just separate that out. And then it has a different nose piece on it that actually, you can use it to stabilize the drill on piles. So that was kind of a new development from IML. It still runs on batteries though, it's not pneumatic. But you can use it above water and underwater, so you don't have to switch drills or anything like that. So yeah, just some slides here on what it looks like. You got your topside dive set up right there. I've got the guy holding the top unit, so he's actually like taking the measurements, and then the guy in the water is just doing the drilling. A couple more pictures of that. This is a weighting inspection using the drill, but that is the underwater unit. It's not the above water unit, but you can stick it just under the water there. A couple things to consider though, like the hand position of the diver and the angle of the drill. Actually, a little mistake on IML, how they built the thing. The tilt sensor's in the topside unit that's on the boat. Like the above water drill, it's all one piece, so it measures the tilt. When they separated the pieces, they didn't put the tilt sensor in the part that the guy holds. So like, you have to be cognizant of that when you're using it, and where your hand, you could technically drill through your hand, so there's some safety issues there. So let's go on to interpreting the data. This is an example of one of the older types of resistograph that has a paper printout. So the horizontal axis is your drilling depth, basically, in inches or centimeters. The vertical axis is unitless, it's just relative density. So the high point's the highest density, and the low point's the lowest density. So you can see on the left where it comes in, you get high resistance, drops off in the void, then comes back again on the right side. So it's just a really good way to visually kind of illustrate it. And this is just an example of a sound timber element data in the IML software that comes with the drill. Just the standard graph produced. I'll discuss what all this stuff means on further slides, but you can add your notes to it. It has the information on your measurement that you took. The blue graph is the drilling curve, and the green graph is the feed curve. So it actually measures two different things, which is the turning and the pushing. So you get two graphs. A couple of other quirks with this. Since the thing is made in Germany, it does dates in the European way. So when we gave this to the client the first time, they thought we did the inspection in the wrong month because it had the day and the month switched. So you have to go into the PDF and manually change that. Here's a good example of how the orientation of your drilling affects your graph. So basically, the orientation in relation to the growth rings can make your graph look different, but it doesn't necessarily indicate that there's a defect with the timber. So if you're perpendicular to the growth rings, you get a more spiky graph, and if you're parallel to the growth rings, you get a smoother graph, but that doesn't necessarily, if you're unfamiliar with looking at it, you might think that might be a defect. So here's another good visual example of that. You can just see how the graph looks on these different orientations of the growth rings. So this second one from the top, nice and spiky as it hits them perpendicular, then it kind of goes near the heartwood, gets parallel to the growth rings, flattens out, then gets spiky again. That could be interpreted, if you're unfamiliar with it, as maybe some nascent decay or something, but it's all solid wood. So there's a lot of kind of interpretation necessary with this. This is a laminated timber beam. So you can kind of see you get the good spikes in the growth rings. There's a little knot or the heartwood there on the left, and then hits a knot on the right and gets a big spike in resistance. So zero resistance would be decay resulting in an internal void. Very high resistance areas could indicate a knot. If it's too hard, the drill will actually retract, or the bit will break if something is too dense. Rules of thumb that are useful but could vary depending on the species and the drilling tool used, so you should exercise caution basically in interpreting the data. So another kind of visual example here. Some of the limitations that we'll discuss later is that the needle can actually follow cracks and splits, which might be misinterpreted as rot. If the drilling would have been 90 degrees, you would have seen a dip in the resistance at the location of this crack, as opposed to a drop-off in the resistance. So now we can talk about a little more how some examples of how you actually rate bridges with this, and this is some examples from ITD. Basically, you make some assumptions. You assume that it's uniform and circular and in the center of the pile, which isn't always the case, but for the sake of calculations, you can basically plug it into a simple calculation and calculate the amount of section loss, or you can use a tabular form like that. So it takes your linear measurement and converts it to an area, basically for the purpose of rating it or load rating it. Yeah, agency defines the NBI. ratings in this case. So you got your rot in inches and your rot by area gives you your MBI rating. This is just a graphical example of the representation, the assumptions that you make, basically calculating your area of decay, the most important thing if you're doing any load rating. There's lots of different ways to sort of display this data. On the left there is a tabular format and like how we would correspond that back to those condition ratings I showed earlier. So now you can take the information, lump them into a category, display it all in a way that's easy to understand, see which ones are moderate, which ones are severe. This is MOTEMS, this is actually the marine oil terminal standards, but you could do it with any standards. Best practices and limitations. Basically the best practice is to use these in conjunction with traditional inspection methods. But I mean, it is easy to use and set up. It's easy to send somebody out and get a lot of data pretty quickly. You're gonna wanna record the locations of everywhere you do the drillings. You're preferably take a photo of each location too, and have plenty of extra drill bits. So lots of little nuances an inspector will learn if they do a lot of these. You can slow down the drilling speed to prevent breaking a bit if it's really dense wood and stuff like that. Another key best practice is that you really want to take enough measurements to fully quantify the defects, because it's really easy to just drill one spot, see one thing that looks like a void, and then say you have basically a failed pile. What you really want to do is take multiple measurements in multiple locations, maybe some different angles, so you can really quantify what that internal void might look like. This is just an example of an inspection plan that you would probably want to come up with. This is again from ITD, but best practice is to just make a plan for each bridge, note your locations on there, note the measurement, have your cross sections and all that stuff. This would be a superstructure example. Substructure, annotate everything, put the type of device, all that good stuff. And then usually you append the raw data graphs to your report. So this is something that you normally would do on maybe high profile bridges or bridges that are in poor condition or an initial or baseline inspection. Talk about some of the limitations. I mean, I said that you can easily and quickly gather a lot of data, but at the same time, for very large structure, it can be quite labor intensive, especially if you're doing multiple drillings. If there's a lot of defects and you have to really quantify those, it can get to be a lot of work. It still doesn't give a complete picture of the entire section without multiple borings. Some of the things like we talked about earlier, it can follow the grain of the wood, which we'll see in a little bit, or it can follow a crack, or it can hit a nail or another obstruction. Because they are pretty flexible. Small pockets of decay could be missed. For the underwater unit, has its little nuances. You have to keep the compressor running and stuff like that. And the standard drill is not waterproof. Added this slide in here. If you look on the left, that's the drill, and on the right, it actually did a full 90-degree turn and came out the bottom. Definitely something that an inspector has to be cognizant of in the field. You can get basically false measurements if it follows the wrong angle. You can think the pile's not the right size or the defect isn't the right size, stuff like that. And you do have to be cognizant of the angle that you're actually drilling into the pile, because that affects your area calculations, stuff like that. Both of these voids were discovered underground, so you can see actually the ground line there on the pile, and the voids are underneath that, and the measurements were taken just above that though, so it's really easy to miss stuff that might be buried. This was an example from Montana on the right. That's pretty interesting. You can actually see the heartwood and the knots in there, but everything else is totally rotted out. So it's just sometimes it's good to get a visual example of what the data might be telling us. Quick run through a couple quick case studies. This is a bridge in Camas County, Idaho by Fairfield. I think it's 3-span bridge, a lot of water in it. It was a routine inspection, not a dive inspection, but so we could drill the tops of the piles. Getting a little old, 55 years old. It's all timber. It's already posted for load. It was rated fair. Rural area, so there's not a lot of traffic, but they do have a lot of farm equipment on this one. So you can see some surface weathering, some checks, some surface defects like that. But this pile actually sounded sound from the old traditional hammer test. So we'll see what that graph looks like when I drilled it. So this was the measurement from that pile. Basically, it had 2.5 inches of sound timber on the outside, a huge decay area in the middle, then picked up again. The little blip in the middle there is probably the little remaining core of heartwood. Big mistake in interpreting this data. If you look at the wood inspector in the upper right, you might not be able to see it, but it says cavity detection 60%. That's 60% of the linear area. It's not, or the linear length. It's not an area calculation. So you have to take that and put it into your graph or your calculation to actually get the true measurement. It actually will tell you the length of the cavity though, so it's 7.79. It's just about 8 inches. The effective length, so it's a 13-inch pile, so you can use all these in the next slide to actually come up with your rating. You take that information, you got your pile diameter on the left, 13 inches. You got your rot, which we saw was 8, and then that can calculate your percent rot by area, about 38%. That puts that condition state in a 4. Here's an example of a check in a timber girder. So you can visually see that there's a check there, but how do we quantify that check? It'd be kind of hard to tell traditionally. So you drill in right above it, and you can see pretty easily. Really the check is about 1 inch in there, and it's about a 1/2 inch wide. So checks are different than decay, obviously. So this is a classic check indication where you get a smooth drop off coming down and then right back up. That just kind of shows that gap. So then you can annotate that yourself and put 1/2 inch check and put your comments in that for the inspection report. And then how would we rate that? So ITD has their method that checks and shakes penetrate 5 to 50% of the member. That was a 1/2 inch check, so that would be a condition state 2. Final slide is just kind of, I guess it maybe ties into the previous presentations a little bit, but the theme, big data, right? So now you can collect a lot of data that's actually quantitative, and you can start using that to manage your inventory better and hopefully make better decisions, put the maintenance money where you need it. The funds could be put somewhere else where it's more needed. So there you go, powerful new tool, accurate, compact, portable, cost-effective, rapid. You still have to have a person with a brain using it, and it still needs to be combined with traditional inspection methods. It's just another tool in the toolbox, but it's a powerful one. It's not a panacea for all timber inspection needs in the world, but it's definitely helping bring more information to bridge owners. So that's it. Thanks. It probably won't affect the actual reading very much, but when they do get dull, they'll tend to break or go the wrong direction, stuff like that. So yeah, you got to kind of look at how dull they're getting and then replace them every once in a while. I don't think it'll make a huge difference on the relative resistance, though. Yes, the question was that some piles are treated, so does that affect the data or the outcome at all? I don't think the creosote coating or anything like that has had a significant effect on any of the data that we've gathered. It doesn't really affect the density of the wood. When you're talking about a void versus sound timber, like it's such a massive difference in density that something like a creosote treatment doesn't really affect it. Basically the question was, have we used it to do basically like establish a baseline inspection for future use for a client? Yeah, the answer is yes. I mean, that's kind of pretty much what we're starting to do with the owners that we're working with, is that then this can be compared in the future. Yeah, I mean, that's kind of the purpose of a lot of what we're starting to do with them. I guess the two types of situations would be like they want a broad inventory of all the bridges they have, or they suspect some kind of defect in a specific area, so you can target your inspection there. So it's kind of like one or the other. So the question is, do you have to calibrate it? Yeah, you do have to calibrate it, but you send it to IML once a year, or if you're using it a lot, like quarterly or biannually, something like that. It's a tool, it's a precision tool just like anything else, like ultrasonic thickness or something like that. So yeah, it needs maintenance and calibration and all that stuff. But it's a pretty robust tool. Question is, species of wood, does that make a difference? Yeah, it makes a difference. Softwoods, hardwoods, different types of things. It's something that you have to take into consideration. Like in the Northwest here, most of the bridges are a specific species in a specific age. They were all built at the same time. They're all softwoods, But if you had some kind of situation where that maybe there was something different, or you suspect there was something different, that'd be something you'd probably want to factor into your investigation. I think the above water drill's around $8,000 and the underwater drill's like $14,000. Not terribly expensive in the grand scheme of precision inspection tools. There's some different features like that wood inspector feature, like that's technically, but they're pretty good about throwing that stuff in if you need it.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.